Okay, so this is discrete optimization and mixed integer program. We'll talk about MIP. So this is one of these magical tools that we have in optimization. So it's going to be very different from what you have seen so far. And this is a tool, when it works, it's really amazing. And sometimes it works, sometimes it doesn't. But you'll see it's really a magical tool. So what I'm going to do in this lecture is give you a basic introduction to mixed integer program. Okay, we call them MIP. Okay, I'll talk about MIP all the time today, and then we talk about branch and bound, which is the basic technique to actually solve them. Okay, basic introduction. This is a big field. What I want to give you is a feeling about what this is about. Okay, so this is an integer program. So what you have to think is that it's like linear program. Okay, so like linear programming, the only difference is that the variable here evolved to be integers. Okay, so we still have, an objective functions that we are minimizing, and we have n variables and m constraints. Okay, so you see the n variables, you see the m constraints. All these constraints are inequalities. Okay. So the variable are constrained to be non-negative, okay, again, okay? And then we have these additional constraints that they have to be integer values, okay? So and this makes a huge difference in practice, of course, okay? So we'll talk about a mixed integer program when not all the variables have to be integers. Some of them can, and some are and some aren't, okay? And that's essentially a mixed integer program. So you have some values that are, like in linear programming, they can take, rational values, real numbers, and then some of them are going to be integers, okay? So, and that's why you call it mixed. It's the mixture of these two types of variables, okay? But once again, a big thing to mention here is that the constraints are linear, they are inequalities, and of course we are minimizing. Of course, all the techniques that I've shown you for linear programming are still working, right? Maximizing is easy to do. You minimize the negation, writing equations or, inequalities or equations in the equations or inequalities are going to be done exactly like we did for linear programs. And of course, if you want a variable which can take negative value, you can always use a difference that we have done before. Okay, so most of the same technique, but what is key is that the constraints and the objective function are linear. But now some of the variables can be integers. Okay, so the difference between having integer variables or not having integer variable is big, right? So that's the gap between being polynomial time and NP complete. Okay, so this is a huge difference. As soon as you introduce these integer variables, okay, so the entire complexity of the problem changes. And for most people in industry, sometimes it's a big difference, right? They say, oh, but it should be easier. There are fewer integers than there are real numbers. But no, having integers is what makes this problem really complex. Okay. So this is an example that we have seen before, right? The knapsack example. This is a mixed integer program. Okay, so we have a linear objective function. The variable xi are constrained to be 0 and 1, and they have to be integer value. We want to take the item or not. Okay, it's not a fractional value. And of course, we had this linear inequality. Okay, so that's the most simple, in a sense, mixed integer program that we have. Okay, so what we're going to do now is look at warehouse location. We have seen this problem before when we were doing local search. And what we're going to do is develop a MIP program for it. Okay, so I'm going to go over what the problem is again, and then we can see how we design a MIP program. Actually, we'll come back several times to this problem. Okay, so what we had there is that we have various locations where we can open a warehouse. Okay, so when we open a warehouse at a particular location, we say we open that warehouse. If we don't put it there, we basically say that it's closed. Okay. And then we have a bunch of customers, around, all over the place, okay? And the goal is actually to choose which warehouse is to open such that you can serve all the customers. And every one of the customer will be allocated to exactly one warehouse. Okay. Now, what you want to minimize is the cost of opening this warehouse and maintaining them. That's a fixed cost for every warehouse. And then you have the transportation cost from the customers to the warehouse. Okay. So you will want to minimize the sum of these two things. Okay. So that's the problem. Okay. So this is one solution where we open one warehouse and we serve all the customers with that warehouse. Okay. This is another solution where we open two warehouses. Okay. And the customers are served, in the way which is depicted here. But once again, I want to focus. I want to mention the fact that every one customer is assigned to exactly one warehouse, okay? And this is another solution with two warehouses. It's a different customer allocation, okay? So now the question is, can we find a MIP model, okay, for warehouse location, okay? And so once again, it's like for constraint programs. It's going to be easy, right? So the only three things that we have to do is find what are the decision variables, and then we have to express linear constraints because we are in a MIP context in terms of this decision variable, and then express the objective function, which is also to be linear, okay? So can we find that for warehouse location? Okay, and obviously the answer is yes, otherwise I wouldn't be talking about this problem, right? So what are the decision variables? Okay, so in this particular case, we are going to use two types of decision variables. Okay, so the first type is going to basically be associated with every warehouse. Okay, so so this is what we want at the end. We want to know, which warehouses we open. Okay, how many and where. Okay, so we'll have a decision variable xw for every warehouse w, and that variable is going to be 1 if that warehouse is open. Okay, so that means that we are building the warehouse at that location. Okay, it's 0 if we just don't build the warehouse at that location. Okay, so that's the first type of variables that are going to tell us where to build these warehouses and how many. Okay, now we need a second thing, right? So we need for every customer to know which warehouse it's going to be allocated to. So we are going to use a second set of variables, which we call the y variables here. Okay, and ywc is going to be equal to 1 if customer C is basically served by warehouse w. Okay, and 0 otherwise. 0 would mean, okay, warehouse W doesn't serve customer C. Okay, so once again, two types of variables, whether we open a warehouse or not, that's the X variables, and the Y variables is going to tell me for a pair customer's warehouse, are these two guys connected? Is this warehouse serving that customer? Okay, so now we have the decision variables. The only thing that we have to do now is express the constraints. Okay, so what are the constraints? Okay, so think about it. What are the constraints in this particular setting? Okay. Now, there is one constraint which is really important that we don't want to miss, is that we can serve a customer with a warehouse only if that warehouse is open, right? So we don't want to connect a customer to a warehouse that doesn't exist, right? So that's a very simple constraint, okay? But it's very important. Otherwise, we wouldn't have a solution. And the second one is that we want to make sure that the customer is served by exactly one warehouse, okay? So we have to make sure that the customer is served, but it can only be served by one warehouse. Okay, and so essentially that's the second type of constraints that we have to express. Okay, now we have to express these constraints as linear constraints. Okay, and that's what this slide is showing you. Okay, so the first constraint telling you that a warehouse has to be open to serve a customer is a simple inequality with the two types of variables. Okay, so we are basically saying that ywc has to be smaller or equal to xw. What does that mean? Okay, so if we close the warehouse, so that means that we close warehouse w, so that we don't build a warehouse, that means that xw is 0, right? If xw is 0, then it's wc is going to be forced to be 0. We can't actually serve that customer with that warehouse. That's part of what we want, right? And if xw is 1, that basically means that the warehouse is open. We can use it, but that doesn't mean that we have to allocate customer C to that warehouse, but we can. Okay, so that value is going to be 1, which basically means that the variable ywc is free. It can take value 0, it can take value 1. That's the meaning of that constraint. Okay? So in a sense, we are encoding the relationship between these decisions using an inequality in this particular case. And this works well because these two variables take 0, 1 values. And we'll come back to the fact that in a MIP, a lot of the decision variables are going to be 0, 1. Okay? The second constraint that you see there is basically telling us that a customer should be served by exactly one warehouse. And what we're going to do is we're going to look at one customer, we're going to look at all the possible warehouses, and we're going to make sure that the sum of the variables that are basically denoting whether that warehouse is serving that customer is equal to 1. And that's what you see there, okay? So you see a sum for all the warehouses, and then you see the variable ywc, okay? So that basically means is W actually serving customer C, okay? So you have the sum of all these guys, and they have to sum to 1, okay? Once again, these guys are 0, 1, so that basically means that one of these warehouses is going to serve that customer, okay? So beautiful, we have a model if we can express the objective function. The objective function now is the sum of the fixed cost and the transportation cost, okay? It's reasonably easy to state. What you do, this is essentially the fixed part, okay? So what we are doing is the sum for all the warehouse of the fixed cost of the warehouse, okay? Times whether the warehouse is open or not. So if the warehouse is closed, there is no cost. If the warehouse is open, we incur a cost of CW. Okay, and then the second aspect here is basically the transportation cost. We look at the pair WC, and if And if W is serving C, that variable Y is going to be 1. So we want to incur the transportation cost TWC. Okay, so that's what we have to do. Of course, if the variable Y is 0, then essentially, there is no cost incurred. These two things are not connected. Okay, so now, these are the transportation costs. Okay, so fixed cost, transportation cost. We have the objective function, and we have the entire model. Okay, so this is the entire MIP model for warehouse location. Okay, objective function, fixed cost, variable cost. Okay, then we have the constraints here that basically state that you can serve a customer with a warehouse if you can serve a customer with a warehouse if the warehouse is open. Then you have to serve exactly one customer. A customer exactly once. So you look at all the warehouses, exactly one should serve that customer. And then obviously these two types of variables have to be 0 and 1. Okay? We open a warehouse or we don't. We serve, the warehouse W serve customer C or not. Okay? And that's the entire model. Okay? So it's interesting when you look at these models that the variables here are 0, 1. Okay? And I'm going to come back to that. But we could have another essentially model where we could think of, instead of having all these 0, 1 variable YWC for all the warehouses, why don't I have simply a variable YC which denotes the warehouse that is serving customer C? Okay? Now this is a question for you. Okay? So think, try to build a MIP model using a decision variable which is YC, okay? And see what the challenges are. It's a very interesting exercise. Try to see what is going to be tough if you use these decision variables instead of the 0, 1 variables that I've shown you. Okay, so the thing is that in general MIP models love 0, 1 variables. Okay, so you'll see a huge amount of 0, 1 variables in MIP model. You'll see typically very few integer variables. Okay, the integer variables are typically going to be 0 and 1. So it's like MIP models like to have decisions which are actually yes or no. Okay, so very different from constraint programming model in that sense. Okay, but the good point is that once you have these 0, 1 variables, expressing linear constraints is typically very simple. Okay, so in a sense, you use these very simple 0, 1 variables, and then all the constraints are, as simple to state in general. Okay, so sometimes they have many indices, but they are easier to state. They are easy to state. Okay, so it doesn't mean that modeling in MIP is easy, and we'll see some of these issues later on. So there are still many possible models that you can design. What are the basic decision variables that you're going to use? What are the constraints? What are the objectives? Everything that we said for constraint programming is still valid. Finding a good model is not necessarily easy. Okay, and so we'll see some of these things in a moment. Actually, the next lecture. Okay, so now we have a beautiful MIP model. How do we solve them? Now this has been an active research area for many decades, and it's still a very active research area. It's a fascinating area. Okay, and so one of the basic techniques to solve MIP problems, okay, is to use branch and bound. Okay, remember branch and bound? We saw that first lecture. Or second lecture. You have bounding and branching. Okay, bounding is what? Is finding an optimistic evaluation of the objective function, or optimistic relaxation. We love relaxing, right? And then branching is when, is basically splitting the problem into subproblems and you apply the same algorithm on the subproblems, okay? So this is the basic 2 steps. Now, what is nice about MIP models is that they have a very natural relaxation, okay? Which is linear programming. And that's why we talked about linear programming so much. We have this linear relaxation that we can use as the bonding as the bonding part of MIP models, of branch and bound for MIP. Okay, so the key idea is that you're going to remove the integrality constraints and you have a relaxation. Okay, so this is the only thing that you do, right? You look at this big MIP model. If you remove the integrality constraints, what do you have? You have a linear program. You can solve that very fast. And that's what we're going to do. Okay, so the bonding part, the optimistic relaxation, is going to be basically relaxing the integer constraints. You enlarge the set of values that the variable can take, so it's a relaxation. Okay, so basically a branch and bound for MIP models is going to be solving the linear relaxation. Okay, at a particular node, you're going to do that. You're going to look at that node. You're going to say, "Oh, I want to solve the linear relaxation." And if the linear relaxation is worse than the best solutions you have found so far, you can prune that node away. Okay, it basically means that the associated subproblems to that node is provably suboptimal. You can get rid of it. Okay. So if not, okay, so if you are basically looking at this linear relaxation more closely, and you are looking to see if it has all integer values, which can happen, right? And if that happens, that means that in this large space of solution, the linear programming relaxation had chosen an integer value for all these variables, and that means that, obviously it's a solution to the overall MIP problem, well, for that node, right? And so essentially you have found a feasible solution, and you can update the best solution you have found so far. Okay? Now, if none of these two things apply, then you need to branch. Okay? And the interesting thing about MIP models is that they are going to use the linear relaxation to drive auto-branch in general. Okay? And so there are many ways to do this. Okay? So I'm just going to mention one here, but this is also a very active area. How you branch? What do you use? How do you use the objective function? Do you use the constraints and so on? But this is the simplest scheme that is using the linear relaxation. So what you're going to do is you're going to look at this relaxation, and you know that some of the integer variables have a fractional value, and they should not. Okay? So what you're going to do is take one of those, okay, which has a, let's say x, which has a fractional value f, and what you're going to do is create two subproblems. Okay? One of them is going to be saying that x has to be smaller or equal to the integer which is the largest integer which is smaller than f. Okay, so that's the floor of f. Okay, and that's one of the subproblems. Okay, and the other subproblem is going to say that x is greater than the ceil of f. That's the smallest integer which is larger than f. Okay, so these are two subproblems that you can add to the set of constraints that you have, and then you repeat the branch and bound. Okay, so the key point here, if you remember constraint programming was obsessed with constraints, okay, and was basically branching on the, using feasibility information. Here we are obsessed with the objective. We are getting this good, hopefully good relaxation of the objective, optimistic evaluation of the objective. And then what we use is we use this linear relaxation, which is like, this is like a very good solution, okay, but it's not feasible, and trying to use that for branching, okay. So in a sense, we are branching using optimality information. Okay? So summarizing what I just said, okay, so we are basically focusing on the objective here, okay? Once again, I'm exaggerating. Of course, a MIP system in practice will also focus on some of the constraints, but it's good to exaggerate to, drive the point home here. So we are basically focusing on the objective, and the relaxation gives you an optimistic bound of the best value that the MIP can ever get, okay? The pruning is based, obviously, on the objective and suboptimality, okay? So when you detect that the linear relaxation is not higher than the best solutions you found, not better than the best solution you found so far, you just prune it away, okay? And obviously the relaxation has been obtained by relaxing the integrality constraints, okay? And we have a global view of all the constraints, So in constraint programming, all the constraints were acting, independently. Here, we relax all the integrality constraints, but when we look at the constraints, we look at them globally, okay? So we have this linear program which basically look at the constraints globally, but they just have removed the integrality constraints, okay? So in the knapsack, in a sense, so when you look at the relaxation, what we did, this is basically the MIP model for the knapsack, and the relaxation is only looking at these, 0, 1 that you see there, okay, and basically replacing them by the fact that, it doesn't have to take the value 0, 1, it can take any value between 0 and 1. Okay, that's the linear relaxation. And we can do that for any MIP model, right? So we just remove these integrality constraints. Okay, now, so in the case of the knapsack, the linear relaxation is the same as the greedy approach that I've shown you, right? Order the item by the most value per weight, okay, and select them in that order, okay, until you get a fractional value, and you take that fractional value to get a relaxation. So that's what the linear programming relaxation is going to do. So I'm going to talk a lot about this linear programming relaxation in the next couple of classes. It's a beast, and you'll see it has very interesting behavior. Okay? Now, when we branch with a fractional value, and essentially in this particular case of the knapsack, the fractional value is going to be the most, the item with the largest ratio that we can't actually fit in the item. We fit all the items which were more valuable per weight, right? Better ratio, okay? And then we are basically looking at that last item that we would want to put in the knapsack, but we can only put a fraction of it. That's essentially how, the item we're going to branch on, because this is the only item which will have a fractional value. Okay? Now, the question that I have for you to think of at this point is that, we're going to take two things. These are 0, 1 variables, right? So it's going to be, so when you run the fraction downwards or upwards, what you're going to get is essentially 0 on one side and 1 on the other side. So we are going to not take the item or take the item. So when we don't take the item, can you think of what the linear relaxation is going to do? Okay? So a lot of the games in MIP is going to figure out what this linear relaxation is going to do. And it's very capricious, you'll see. Okay? So in a sense here, what I'm asking you is that if we don't take the item, what's going to happen? Okay? Or if we take the item, what's going to happen to this linear relaxation? Can you figure that out? Okay? So in a sense, the question that I'm asking you is, which value is going to become fractional if you don't take the item? Okay? Think about it. I decide not to take the item. All the items that were more valuable, what's going to happen to them? Well, you're going to still take them. And then what you're going to have is a fractional value for one or more items later on. Okay? So that's what's going to happen if you don't take the item. If you take the item, what's happening? Before you couldn't put this item in the knapsack. Now you are deciding, I want to take that item. So that means that some of the items that were before, you won't be able to put inside the knapsack. Okay? And so there is going to be a fractional value for an item that was more valuable that's now going to be fractional. Okay? So this is the kind of reasoning that sometimes you need to think about, what is the linear relaxation doing? Because that will give you insight on how to actually improve your models. Okay? So this is a very simple illustration because this is a really, really simple example. But it's going to drive 2 points home. Okay? And you'll see them. So once again, so we had basically these this knapsack with 3 items. Okay? So the value of the item is VI. The weight of the item is WI. You had item 1, 2, 3. Okay? So the most valuable item is item 3. Okay? 35 divided by 3 is pretty good. Okay? Above 10. Okay, so 45 divided by 5 is what is 9, and 48 divided by 8 it's around 6, right? And so therefore, this is the most valuable item. That's the next one, and this is the least valuable item from a weight, value ratio. Okay, so at the top of the tree, at the root node, what you have is a value of 92, and that value of 92 is basically obtained by selecting item. Well, I think we can let the linear relaxation do this. And this is what the linear relaxation does. Okay? So the linear relaxation is going to take, value 1 for x1. I'm taking item 1. I'm taking item 3. Okay? So these are the two, items with the best ratio. And then I take only a fraction on the second item because I can't put the entire item in. Okay? And, once again, this is 5 and 3. This is 8. I can take only a quarter of that guy. And this is all you get. This value, because you sum 45 and 35, that's 80, and then a quarter of 48, that's 12. That's the value of the linear relaxation. So this linear relaxation is basically giving you this solution and that particular value. Okay? What are we going to do? Okay? I told you, we look at this thing and we look, what is the fractional value? And in this particular case, it's item x2. Okay? So we're going to branch on x2, and we're going to create 2 subproblems. Okay? One where x2 is 0 and one where x2 is 1. Okay? What happens if x2 is 0? Okay? So that's the node that you see over there. Okay? Now the linear relaxation is 80. Okay? You can select only item 1 and 3. Okay? So we solve the linear relaxation at that node, and what do we obtain? X1 is equal to 1, x2 is equal to 0, x3 is equal to 1. That's the linear relaxation. The linear relaxation here is finding, an integral solution. We know that we don't have to branch anymore. We are fine. Okay, this is the best we will ever be able to do. It's all integral. Okay, so we don't have to branch anymore. It's done. Okay, so the linear relaxation here is telling you when to stop branching in a sense. Okay, so we have found a solution with a value 80. Okay, the other things that we wanted to do is basically, choose x2 is equal to 1. Okay, so we basically fix the value of x2 to 1. We solve the linear relaxation again, and the linear relaxation is going to give us a value of 71.33. Okay, you see that now there is this value of x3 which is fractional. Okay, it was actually not fractional in the original relaxation. Okay, so we know that we would have to continue branching, but what we have seen here is that the value of the linear relaxation is 71. The best solution that I have is 80, so I can actually prune that node away already. Okay, so with one branching, essentially, I solved this problem optimally. Okay, so this is essentially illustrating the various concepts here. At the particular node, you solve the linear relaxation, okay? You look, the value of the objective function of the linear program is basically giving you an optimistic evaluation of what the MIP can do, okay, at that particular node, okay? And then you look at the variables over there, and you take a fractional variable to actually branch, okay? And then you branch left and you branch right based on that fractional value, okay? Now, one of the questions that you have to think of is, when is this branch and bond going to be effective? Okay? Well, it's going to be really effective if the value of the linear relaxation is tight. It's very, very close. If the linear programming relaxation is very close to the optimal value of the MIP. Okay? Is that sufficient? Think about it. Okay? So if I tell you, I guarantee, okay, that this linear relaxation is going to be 0.5% always of the best value of the MIP, is that sufficient for the MIP to actually behave nicely all the time? Okay? Question for you. Okay? I wish we had quiz in this class. We don't. But anyway, so think about it. Is it sufficient? Okay? So what is a good MIP model? A good MIP model is going to be a model which is a good linear relaxation. It's not sufficient necessarily. Okay, I haven't answered that question, right? But this is a necessary condition. You want a model with a very good linear relaxation. Why? Because you're going to prune the search space much better. Okay? Now, which variable should we branch on? So we have a lot of variables. Assume that we have plenty of variables with fractional values. Which one are we going to branch on? Okay? So one of the good heuristics is to branch with the most fractional value. Okay? So why? Why would we do that? Well, once again, exaggerate. Assume that you have a variable which is not very fractional. Okay? So it's like, 0.999999999. Okay? And it can take value 0, 1. Okay, so when it's 0.9999999, okay, I hope I use the same number of 9s, but that means that it's really close to 1. Probably branching there doesn't make too much sense. If a variable is 0.5, what does that mean? That means that the linear relaxation is saying, maybe I should take this item. Maybe I should not take this item. I don't really know. Okay, and so therefore these are the type of variables that you need to branch on. Okay. So this is a basic introduction to MIP. Okay, next time we're going to see really cute things on how you can actually build MIP model. What does it mean to be a good MIP model? Okay, come back. Thank you.